Welcome back. We're going to be doing a couple of examples of some of these collision and energy things. So the first one is this idea of so shooting a gun with a bullet, and there's several things going on here. We're going to analyze what would happen if the bullet entered into a block of wood, and let's say that wood was on some ice, right? So the friction here would not enter in. Maybe this is a freshly oiled ice patch. So obviously the bullet's going really fast. When it hits the block of wood, it goes 10 centimeters per second. Now let's think about this situation even here and just kind of analyze it in terms of collisions and energy. What's making the bullet fly? Well, it's collisions as well, right? So collisions even there. What happens in the gun is that gases explode, and so the expanding gases cause kinetic energy in these gas particles, and that kinetic energy transfers to the bullet and causes the bullet to fly. Now, you think all of the kinetic energy from the gases transfers to the bullet? Clearly not. We have sound, bang, really loud. You have heat. You know that the gun will get hot. I mean, it's basically an explosion, kind of fireball comes out here. So there's a bunch of heat. So the kinetic energy is kind of going to go a lot of different ways. Okay, we've got sound. You know, the gun will move backwards. So even the gun itself, you know, there's some recoil that way. You got heat. All right, so that energy transfers in a lot of different ways, but enough of that kinetic energy is going to transfer to the bullet, right? And so the bullet flies out. And so here's the question right now. Could we figure out the actual initial velocity of the bullet? And then maybe from that, could we actually find out the initial kinetic energy of the bullet? So these things are all possible. So first of all, let's look at the idea of solving for the initial velocity of the bullet. Well, this one's going to be pretty simple because we have mass, and we have velocity. So when you're asked for an initial velocity kind of thing, and then, or maybe you're just asked for a kinetic energy, you're going to have to use the conservation of momentum to find your velocity and then incorporate that into your kinetic energy equation, because we understand that the kinetic energy here, when the bullet hits it, is probably not going to be the same. This is definitely going to be an inelastic collision because the bullet is going to enter into the wood. So a bunch of the energy is going to transfer into, you know, splitting this wood open. We got heat. We got all sorts of thermal energy stuff going on here and changing shape. So the energy is going to go a lot of different ways when it hits this right here. So we couldn't use the kinetic energy of this to figure out this because we can understand that this is going to be a different kinetic energy. This is definitely an inelastic collision. So let's look at my energy, or my momentum initial and my momentum final. So my momentum initial is going to be 8 grams, which is 0.008 kilograms, right? Times my velocity initial, and so my velocity initial in this case is an unknown, is going to equal then my new mass, and so my new mass is actually going to be these together, so it's going to be 9.008 kilograms, because the bullet is going to stick in the piece of wood. So my new mass is going to be my mass of my block and my bullet. So remember, momentum is mass times velocity. So this is mass times velocity equals mass times velocity, and this is initial and this is final. And so my final velocity, 10 centimeters per second. We're going to convert that to meters per second. So that's going to be 0.1 meters per second. Right? So let's go ahead and multiply these together and divide by this, and we'll find that my initial velocity of my bullet is 1.13 times 10 to the second meters per second, or you could just say 113 meters per second. So clearly the bullet's going a whole lot faster than the mass is here. And if we were to analyze the kinetic energy initial and the kinetic energy final, we would find that the kinetic energy final is less than the kinetic energy initial. So let's go ahead and do that real quick. So the kinetic energy initial is going to equal the mass of the bullet, which is 0.008, times the velocity of the bullet, which we just discovered, which is 113 meters per second squared, divided by 2. So the kinetic energy initial is going to equal 50, oops, I drew that backwards, is going to equal 51.1 joules. All right, so there's my initial kinetic energy. Now my final kinetic energy is going to equal the mass of the bullet and the block. So I have 9.008 times my final velocity, which was 0.1 meters per second squared, divided by 2, and I get my kinetic energy final to equal 0.05 joules. So clearly, most of the energy of the bullet went into other things when it entered in. And so, I mean, that would be the same thing. I mean, that's why a bullet is effective, because when a bullet goes into something, it tears stuff apart, releases heat, does all sorts of damage, doesn't necessarily move something. So this is a big old huge block with a lot of mass, and so when that bullet hit it, not very much of it ended up still as kinetic energy. The rest of that energy all went inside here doing all sorts of stuff. And so there you go. There's the proof of it. There's my kinetic energy final, my kinetic energy initial, and that's how I used the idea of momentum to sort of solve for the parts of this that I didn't know to begin with, and sort of put them into play. All right, well, I hope this helps with your homework assignments as you're doing this. We'll do one more example where we have kinetic energy and potential energy entering into the system.